Good morning or good afternoon, wherever you're calling in from. Hello, everyone, and welcome to Webinar Wednesday. My name is Jeff Jezzard with Vector Construction, and I will be your host for the webinar series. Today, I am very excited to introduce part 2 of our webinar series brought to you by the Concrete Preservation Alliance, Strength in Repair, Next-Gen Strategies for Concrete Longevity. The series dives into concrete repair solutions that are designed to equip industry professionals with the latest advancements and innovative methods to restore, reinforce, and extend the life of your concrete structures. Today, we will be talking about mastering injection and grouting, innovative solutions for crack and void repairs. This is the second of a 4-part series where we will explore the various injection and grouting methods available to repair cracks and voids in or under your concrete structures. So whatever you're dealing with, minor cracks or significant voids, this session will help equip you with the knowledge to tackle concrete repair with confidence. This program is brought to you by the Concrete Preservation Alliance. We are a coalition committed to advancing best practices in the field of concrete preservation. We draw on our members for speakers and presenters to provide education and awareness to the concrete repair industry. We would especially like to thank our members and supporters from across the globe that make up the Concrete Preservation Alliance and make educational events like this possible. As you can see, here's a list of some of the Alliance members, which has been growing continuously as we move on. One thing we pride ourselves on is sustainability. Sustainability is a big part of what Vector and the Coalition are all about. One of the biggest things we can do in our industry is to keep our structures in place, restore them instead of replace them. On the We Save Structures website, we have the environmental impact calculator. If you are looking at a concrete structure and comparing rehabilitation versus replacement, you can enter the amount of concrete you are keeping in place, and the calculator will give you many facts. For example, the conservation of natural resources, the avoidance of solid waste in landfills, consumption of water, and the creation of carbon. We encourage engineers and owners to use these types of tools when considering plans for their structures. If you registered for this webinar, you're probably familiar with We Save Structures site at wesavestructures.info. You can find the recordings or slide decks of all of the awesome presentations that have been previously done. There are many great series you can find that focus on bridge preservation, parking and marine structure preservation, concrete durability, non-destructive testing, and the design series. Also, please note our next session of this concrete repair series, which focuses on CFRP, which are carbon fiber reinforced polymers, and how CFRP is being used in the industry to strengthen concrete. It's of course on a Wednesday, which is Webinar Wednesday, and is scheduled for January 29th, so please log in to register. Finally, one of the last housekeeping items, what we like to promote along with the webinar is the opportunity to ask questions. Just type your question in the chat area and we will do our best to get to it at the end of the presentation. Mike will answer questions when he's done. We ask that you provide us with your name as you ask the question in the chat function. This is because we are giving away a $100 Amazon gift card to the best question asked. So ask as many questions as you like. And with that being said, it's time to introduce our presenter. We are lucky to have with us today Mr. Michael Kernan. Mike is a close friend and colleague at Vector Construction, where he has worked as division manager of the Illinois office for nearly 10 years. He's been in the industry for 25, so very aware of what we do. Mike is active with ICRI, ACI, and currently sits as the chairman of the PTI Repair Certification Committee. With no further ado, I will turn this over to Mike.
Okay, awesome. Well, thank you, Jeff.
Thank you, Michael.
Introduction. Yeah, so concrete cracking, that's what we're going to be talking today. And one of my famous quotes, I always like to misquote from somewhere else, is there's nothing certain in life other than death and taxes, but of course, concrete will crack. So I think that concrete cracking is more consistent than anything that you're going to find. But man, I get excited about this subject matter. I don't know. I see cracks in concrete all over the place. It draws my attention. I just love trying to dive in and try to understand what was the root cause of that, what happened, how do you repair it, how do you do that? And then my wife nudges me and says, stop doing that, we're in the grocery store, just keep walking. So, and honest to God, that happens all the time. So there is so much going on with what we could talk about when it comes to cracks and voids in concrete, that we're just going to touch on the basics today, just because there's so many elements. We could get into post-tensioning, how that affects it. We could be talking about the different elements of buildings, beams, columns, versus slabs versus elevated slabs, etc. But for today's purposes, we're going to stick with just kind of doing a general overall introduction, and then hopefully we'll leave time at the end for questions. And if we don't have time to answer your question today, we will follow up within the next 48 hours to get you some answers where we can. So thank you again for joining. Sometimes I like reading the slides, sometimes I don't. So you can see from the slides what we're covering today. So I'm just going to launch on here. One of the pieces I find very important when, like I talked about earlier, is like, oh, what caused that crack? What is going on? So I like using this process, the concrete preservation process, but it's really kind of a root cause analysis, understanding it. So identifying issues, I mean, obviously we're here to talk about cracks today, so it's hard to read it probably in that chart, but the crack part is highlighted. And then you go into perform evaluation. And so we're going to talk about that piece coming up here, and determining cause. So these are the different topics that we're going to move along, and then we're going to talk about developing repair strategies, and then an overall kind of viewpoint of how you implement some of the more common repair strategies, and then also get into the quality control piece of things. I went very detailed on this slide, and the reason for it is that you have the ability to download this presentation and reference back to it. There are some fantastic articles out there and interesting journals from ACI, American Concrete Institute, and then International Concrete Repair Institute as well, ICRI. So I just put a few up there. There's even more than that that's available. Safety considerations. We always try to make sure that when we're talking about repairs and evaluations, that we talk about, what we need to do from a safety standpoint. Why is it important to address cracks? This becomes a very common question. It's like, okay, when do I need to start? Does every crack need to be repaired? No, every crack does not need to be repaired. It's part of the natural part. We talked about it with concrete. If you have concrete, it's going to crack. So ACI has developed some guidelines to talk about, okay, when does it need to be addressed and why does it need to be addressed? So let's focus on the why part and spend a little bit of time about talking about there. The primary reason that you're going to see on why a crack needs to be addressed would be when it is exposed to the elements or exposed to water. And so water will infiltrate and move through cracking. Okay, water by itself is not necessarily a bad thing when it comes to cracks in concrete. Concrete's porous, water will move through there. But what you're actually doing is, in many cases, that crack is creating a method by which the water and possibly chlorides, if this is a bridge deck in the parts of the world that are experiencing snow and you have salts, you have chlorides being introduced that way. If you're near the coast or salt water, then you have other, that's a natural source of which the chlorides may be getting there. Chlorides, water, a quicker conduit to get to the reinforcement inside of that concrete, and you're going to find that you're going to have accelerated corrosion. So that's one of the primary reasons. Now, not only chlorides, it could be other chemicals. If you're in an industrial facility, if you're in a water treatment, we have all those people that are today or they're on, and they're representing a large swath of different industries. So there's different chemicals that will be impacting the reinforcement. If you're in an area with cold weather, our friends up in Winnipeg were just talking, did it freeze today? So, or excuse me, did it snow? Well, obviously you start getting into a freeze thaw. So if you have cracking in your concrete and you're allowed to saturate that concrete, and then you get a freeze thaw, you're going to start seeing damage, and that aggregate paste is going to start falling apart. Obviously, some of the cracking may be due to loads. You know, maybe there's too much load being put on. Maybe there's a lack of reinforcement or a lack of thickness. So I won't quite get into everything. And the last one is aesthetics. And a lot of times people don't want to be walking through a building or a garage or somewhere and start seeing cracking in their beams, because even though it may not be a big deal, it causes issues. I did want to pause there for just 1 second, just talk real quick about cracking and aesthetics. A lot of people think, oh, hey, I got crack. I'm gonna either put a coating over the top of it, or I'm just going to paint over the top of it. I just wanted to kind of be clear as far as cracks will transmit through those through painting. It'll transmit through most coatings that you put on, waterproof coatings. You put a 3-part coating on there, and that cracking will transmit through, and that cracking will eventually come through those coatings as well. So, but table 4.1 over there on the right-hand side is a great chart to keep handy, because it talks about the diameter of a crack and when it needs to be addressed based on the exposure conditions. Okay, so there's, for simple purposes, we're going to refer to as moving and non-moving cracks. So concrete, it has, it expands, it shrinks, depending on temperatures, depending on loads, etc. So if a crack is actively moving, that means one or both sides of that is either expanding or contracting on a regular basis. A non-moving crack is one where you don't see really changes in volume of the concrete around it, so the crack is relatively consistent in diameter and not growing. So let's start talking about some of the common cracks that you're seeing. So this photo right here is very similar to one I saw earlier this year when on a new concrete pour. They had poured a roof slab, and they were probably 2 weeks behind schedule, so they were rushing things. And what they did was they poured in the middle of the day, and they didn't spend enough time, and it was a windy day, and they didn't spend enough time making sure that they were taking care of the fact that you're going to have evaporation going on. If you got a sunny day, you have a windy day, you have the factors that you're going to contribute to advanced evaporation of the water. So as that water leaves that concrete too quickly, you're going to have what they call plastic shrinkage cracks. And the plastic is referencing the state of the mortar and at the time. You have load induced. So this is a good example of a load induced crack from this is a bridge abutment, or excuse me, a bridge pier, and you can see here either due to corrosion or just loads in general is starting to crack because of maybe the beam isn't thick enough or something along those lines. The drying shrinkage cracks, the thermal cracks, those are resulting again back to, ACI has a document, and they talk about, the root cause of cracks, and I think it's 43 pages long, and it references about 5 other articles for more information, so you can really dig really deep into this subject. But basically, a lot of this comes down to on this initial shrinkage cracking is that the concrete element that you have, especially when you pour this new, has different forces going on within it. And it's not uncommon to have, as it's drying, to have the outside of it, the surface of the concrete will lose its moisture faster. We talked about with that plastic shrinkage cracking. So as it's losing that moisture, it's having it's creating some internal tension because of that shrinkage, what's going on. But the inside of that concrete element may still be under compression, so the forces are going otherwise. So when your internal tensile stresses from this change between compression and shrinkage overcomes the tensile strength of concrete, that's when a crack develops. Sorry for digging a little bit deep. The engineers are probably saying, hey, that's not deep enough. Some of you guys are probably tuning out at this point going, okay, move on. I don't have a lot of time to talk about all of the different types of cracking, but we'll talk a little bit about corrosion. Corrosion is the corrosion of the reinforcing steel inside of the concrete. As that rebar or steel reinforcement corrodes, and it will expand as it creates the rust, right? So as it expands, concrete has no ability to expand. So that expansion of the rebar will cause cracking into the concrete. And that's a very, very common problem you'll see. A lot of slab on ground, slab on grade, you'll see settlement cracking. And so these are what you'll normally encounter in parking lots. So either under reinforced or poor drainage or not proper prep of the ground. Again, if the ground is not level and that concrete's sitting on top of it and you're applying loads to it, cars driving over it, trucks driving over it, it's going to deflect and crack. So detecting cracks and voids. We can't forget the void part. That's the second part of the presentation. But anyways, obviously inspections. So I'm gonna pick up the space here. So obviously the first part of finding cracks is this visual inspection. So it's an excellent way. Earlier in the slides, I show what a crack gauge looks like. That's a good tool to be able to put up there and to see if your crack is growing. Another tool, non-destructive, NDT is non-destructive testing methodology, is either GPR or impact echo or pulse velocity, and we'll talk a little bit about that. And then the last one, or then some of the destructive manners which you can see for cracking is coring, which is you can see that on the right side where you're actually drilling it in. How deep does that crack go? And it kind of gives you an idea along those lines. So impact echo, the non-destructive technique, is a fantastic test. And I have some examples towards in case studies to be able to show you how useful this is. And it's extremely useful in thicker elements. So if you have piers, pier caps, if you have bases, motor bases, whatever that may be, or thick elements as far as walls, what this process is, I'll get the drawing up here, is that you're creating a sound wave, an energy wave by impacting, by doing a projectile, and you're hitting that concrete with that projectile, a steel ball, at a high velocity. When that does it, it creates sound waves that travel through the concrete. And then you have a sensor array. So if you go back to this slide right here, you see in his right hand, you see the projectile. So that's going to be firing a known weight steel ball at a known velocity at the concrete. And then you have 4 array sensors in his left hand that is picking up that energy wave that's moving through. So pulse velocity is measuring it as it's moving across the concrete, and I won't get really deep into this. And the impact echo, which can be done at the same time with those devices, actually will measure as that sound wave goes up, down, bounces within there. Every time that wave encounters a crack, which is essentially a void, it will impact the speed of which that energy wave is traveling. So as it impacts that wave, the sensors is measuring that, and you're able to get it like a 3D image of how that's impacting, how deep those cracks are, how wide those cracks are. So, okay, so crack void repair techniques. I'm going to go through these and talk about these at a high level. Again, your primary process of what you want to do with repair techniques are you want to seal and prevent moisture intrusion. Almost all of them talk about that. Sealing and preventing moisture intrusion is not necessarily a structural repair because not every crack needs a structural repair. One of the most common ones that you'll see, especially on slabs, is route and seal. So this is classified as a non-structural repair. It will work with either moving or non-moving cracks. Again, walls, curbs, slabs, this is generally where you see it, but I'll walk you through it. I do want to point out that one of the inexpensive tools that you'll have at your disposal for diagnosing cracks is a crack width gauge, and that's what's up in the upper right-hand corner. Those are usually handed out by the hundreds by engineers, and they're very, very handy tools. So route and seal. Now, let me cover some of the important basics. I won't go through every single step, but there is a very important aspect of doing the route and seal, and that is the width diameter ratio when you go to do a repair, because the repair materials that are typically used in this, and you'll have to reference back, are specific that if you're going to have a crack that's you could go up to 2 inches, but if you have a 1-inch crack, then you got to make sure that your width and your depth go together from the standpoint of a 2 to 1. So if you think, okay, it's really deep, but I'm going to go really deep, but I'm going to keep this pretty narrow, that's not going to work out very well. Another important point I want to break out, and it's in the bottom illustration on the right-hand side, is you want 2 points of contact for your repair material. So that means if you have let's just call it for simplicity, the left and right side of that crack, and your repair material is bonded to it, which is the goal. As that moves in or out, contracts or shrinks, excuse me, those are the same thing, or expands, that material is designed to flex with that. Now, if you add a third element and you bond that repair material to the bottom of the crack, let's say your crack's not that deep, but you bond it to the slab underneath, you've now created a third point by which it's bonded. And you can't, it no longer, if it tries to expand or contract, it's going to tear now because it's bonded to that bottom part. So there is a part in this repair procedures that never skip, and that's putting a bond breaker in or a backer rod or something that's in there and prevents that from bonding to the bottom. There's a whole bunch of different materials. I have those listed here. There's elastic to non-elastic. If you're going to use a rigid, make sure that it's a non-moving crack. If it's a moving crack that you're trying to repair, use an elastomeric like a polyurethane. No. So one of the pieces I want to talk about here is in the routing. The routing part is what you reference, is where you're taking a V-shaped concrete blade, usually around a 1/4 inch, and you're expanding that crack out. And this, again, this 1/4 inch V shape that you're grinding is going to give you the diameter, and a consistent diameter, which is important for routing and sealing, because a crack by itself is very inconsistent. It's very difficult. You can see this middle photo, it's not the best one, but at the same time, that crack is very jaggedy. You're not getting any kind of consistency. So if you're moving along and you're routing that out, you're going to get a consistent edge. And then you're going to come along and make sure that that crack is cleaned out, the edges are clean, and then you can come back and apply your sealing material in there. And then, I kind of break down the points about the backer rod, which I talked about already. Okay. Now this epoxy injection, which is a 2-part, you have a resin and you have a catalyst, you mix them together, and you have an incredibly useful tool for repairing concrete. There are so many different types of epoxies. I kind of talk about some of the, I'm not going to go into all of these. I'm going to leave this on a slide for references, and then you can either write it down or download it later. But basically with most epoxy injections, you're doing a structural repair. You're almost like welding that concrete back together. Not only is it repairing cracks, but if you're having honeycombs or voids, this is a phenomenal way by which to get the material into the concrete element that you're trying to repair, because it can travel 3, 4, 5 feet through the concrete even farther and be able to fill and restore voids. The diameter of cracks is everything from what we call hair size, hair diameter to much larger and stuff along those lines. So incredibly versatile. The different types, again, I kind of list here. One of the important things that I talk about here is most of the epoxy repairs that you're doing is a type 4, which is a 10,000 psi strength material for these epoxies. And something I like to explain to people, especially why stiff epoxies are not very good for moving cracks, is concrete, your typical concrete is 4 to 5,000 psi. So if you put a 10,000 psi epoxy resin between the two slabs of concrete and that concrete's moving, that epoxy is actually harder and stronger than the concrete around it. So you're actually, as it moves and it compresses up against it, that concrete will actually crack again. And so you'll have a crack next to a repaired crack because of that moving part. And so epoxies also, once it bonds, has a 7,000 psi. So it grabs and it has a very high tensile strength. While concrete only has, typically I usually use about 300 on the tensile strength, which is the part where you kind of can rip it. Let's top it that way. Important elements for it is when we're talking about epoxies, you have many different types of viscosities. And so you can go very fine to thicker. Many people think, okay, let's go with the lowest viscosity as possible. But if you end up doing that and you start trying to repair your cracks, that ultra low viscosity can start coming out the pores of the concrete. It can go into areas that are unattended. So make sure you right size your viscosity to the repair that you're trying to accomplish. Temperatures of the structures is very important. The size of your voids are very important. Epoxy resins with that catalyst will heat up. And so if you have a very large void and you're putting a lot of epoxy in there, you're going to be generating lots of heat. And when I mean lots of heat, I'm talking in excess of 1,000 degrees if you put too much material in there. So in this photo, I show the pre-repair process. That concrete is 36 degrees Fahrenheit. So just right around maybe 1 degree Celsius. Too cold for the epoxy resins to be able to bond to. So what had to happen was heat and covering had to be applied for this repair before we could get started. And so we able to raise the concrete up to 65 degrees Fahrenheit. And then we are able to start adding our ports to be able to do the repair. So these are things to be able to pay attention to. And there are low temperature resins, epoxies, and there's also high temperature ones as well, because it's temperature sensitive. The higher the temperature, the faster reaction. So if you're in a hot environment, if we're working in a paper mill and it's 130 degrees, if we're using something that's not made for high heat, that epoxy will set up too quickly and it'll gum up our machine or equipment, our injection heads, all of that. So we have to keep those in mind. First step in epoxy injection is that you do not have to V-cut it in most cases. Now, in some cases, it's thrown out there that you could do it, but most of the time V-cutting is not necessary, and we'll get to that. But what is very important is you want to make sure that you grind the surface, and you're doing two things here. You want to create something that's a flat surface. So because you're installing these injection ports, that's on the right-hand side. Those are the injection ports, and you add those ports right over the top of your crack. And so that's why I say V cutting is not always necessary, because you're putting those ports on top of it. So if you make that diameter of that crack larger than it is, then you can have some struggles. But you want a nice flat surface to be able to get those ports installed. Port spacing is determined by the thickness of the element you're trying to repair. So typically, if you have a 12-inch thick wall and you're trying to repair a crack, your spacing in your ports will be about 12 inches. Now, when I'm repairing a base, a concrete base for a motor base, and that is, 6 feet in thickness, well, I'm not going to put my ports 6 feet apart. So the general rule is, depending on the size and the width of the cracks, is around 8 to 10 inches on your separation of those ports. The next part is, so you apply those ports. When you're applying those ports, you're using a small amount of epoxy paste to be able to put those over the top. Next, you're coming along and you're using that epoxy paste to cover the entire crack. And the reason you're doing that is the epoxy paste itself has no structural value to crack repair, but you're creating a seal so that when you're injecting the resin, because you're going to be injecting this resin at a high pressure, you want to make sure that the resin is going into the crack and down through the crack to repair it. You don't want it coming out through the crack itself. 80% of the time when I see failures in epoxy injection, it's because you don't allow this to cure. And they make the epoxy paste in many different forms and fashions. So you pick the one that's suitable for you, let it cure up, and then do the injection. So you see here you have an injection head. That injection head is really important from the standpoint of it mixes the catalyst and the resin together at the head. So you're at that point is when the curing process will start. You're injecting it under pressure. Every situation is different, but epoxy injection is not a race. This isn't, let's start off at 200 psi and just push our way through. That's a recipe for disaster. So start at a lower PSI, work your way through. Your goal is to start seeing, as you can see in this photo here, on the left-hand side, there's a bunch of ports that are in dark color. Those all have resin. All the ones to the right are still clear because the resin haven't reached it. So typically you're injecting until you start having the resin come out to the next port. And then you're going to cap off that port, and maybe you keep injecting if you're getting good flow and kind of moving along. So I included this slide. Stu here was doing a great job, but I wanted to show you on the right-hand side, you can see where the paste was not applied far enough, and the resin is the epoxy resin is coming out through a crack just on the other side of that paste. I won't spend a lot of time here. I wanted to illustrate one of the things that we use epoxy resins a lot on is for filling void spaces under motor bases, or in this case, this is a spillway. So this is going to have high velocity water flowing through it. And they wanted to make sure the stainless steel inserts had no voids underneath it so that they had no cavitation that was occurring. The one on the right-hand side, we drilled and we injected through 6 different ports where the voids were at. That injection job took us nearly 8 hours to get that epoxy resin to move through that 4-foot opening, just to make sure all of those areas, because it was well installed very well, but there's just a few areas of voids, and we needed to do some vibrations and really move that resin along slowly. Next piece I want to talk about is chemical grouting, which is also called urethane grouting. This is a great solution for moving cracks because most of the urethane grouts that are being used, the chemical grouts, are flexible in nature, have elastomeric. So as that crack compresses or expands, it will move with it. It has very, very good bond strength as well. And it also does a great job of filling voids. When most of these urethanes are waterproof, that you're using, so you're creating a waterproof barrier. So if you look in that cup, I know this is a terrible photo. There's some really good videos of this. If you have a cup with a little bit of water or a half of just the bottom of that with water and add a small amount, that resin will expand up to 5,000 times. So that resin will grow and fill the voids. There's a lot of different kinds of urethanes. I won't really go into all of it, but you can customize it by the solution. A lot of the most common you'll see is what we call the single component. So the urethane is the catalyst for that sets it off from foaming is water. And then if you're in water treatment area, or you're working with something with potable water, then you want to make sure that you're looking for urethanes that are drinking water safe. Urethanes are done differently. In epoxy injection, you use ports. In urethanes, you're using a packer. And so you're drilling in and you're trying to intersect that crack at the midway point through its thickness. And I think the drawings illustrate this very well. And so you're going to drill down at a 45-degree angle. You're going to be X number of inches away from the crack based on the thickness of the crack. And then you're going to be able to install that packer there to get the urethane into that crack. As that image in the bottom right-hand side shows, you do not seal the crack because that urethane will spread throughout there. And if you match the proper material with the crack size, it's going to start foaming and expanding and starting to fill all of that. And that's easy enough to scrape off of the surface. But that's your visual cue saying, yes, I have communication. I'm being able to get this to flow and fill this crack and prevent that waterproof barrier. And then if the water, like in this photo, the water many times when we're doing urethane repairs is actually flowing at the time, which is not a problem. You just match it with the proper material. So you drill your holes, do your injection. As it expands and fills, you can see it as it moves along. It will prevent that. It'll stop the water from flowing. It's amazing. Curtain grouting. So this is, I won't spend a lot of time on this, but this is a wonderful technique, especially when you have a lot of water kind of flowing through. You're getting the urethane on the positive side. So you're drilling through, you're installing lances at a let me get a lance. There's a lance. Get to the image. So you're putting these lances in, and then you're injecting the urethane in the back side of it. So this is where your water pressure is. So your positive side of your water pressure, you're getting it over there. It's putting this urethane coating curtain on the back side of it. The water pressure is pushing that foam, waterproof foam up against the concrete, and you're creating a perfect barrier. So instead of trying to put a finger into the dike on the negative side, you're on the other side of it. So a lot of different processes, a lot of different viscosities here. You could really, if you need real thin, thick, whatever it may be. Let's talk about grouting. We have about 12 minutes before we start getting into questions, so we may have to cut some down. Grouting is fairly simple. I mean, you get many different kinds. It could be a Portland cement, a sand mixture, if you're doing a cementitious one, or you can use also the urethane grouting. And so if concrete has voids underneath of it and you're applying loads, we talked about it, it's going to crack. So by drilling through and installing packers, we can install large amounts of void fill materials, either urethanes or through the cementitious materials, and be able to fill those voids. And when I say large amounts, I've been involved in jobs where we've gone through 30 truckloads of material to fill the voids underneath. So it's amazing. It's amazing what you can do. So soil stabilization is another related subject to this. And so you're using either a cementitious or a urethane to inject into the soil. So you see on the right-hand side, the strength difference, the before and after when you inject it. These photos are a little bit hard to see, but all of this white that you see was injected through the slab into the soil underneath the slab, And so it will fill all of the void space. That viscosity is very low. Fill all the void space and create this this very dense foam that gives that material, the soil, additional strength. And then here's a close-up. So soil, foam. And so it's filling that in. It creates this honeycomb, and you have a much more stable soil environment. And so we can either customize it and create it more like a tight column. And so that's more of a compaction style, or we can use something that has a very low viscosity that just travels and kind of locks that soil together throughout, depending on what your needs are. Think of the compaction style as almost like, putting a grout, or excuse me, like a pile in place. I put in here, I left the word mud jacking because the mud kind of refers to the fact that you could use a cementitious material, or you could use a urethane to be able to lift a slab. And sometimes people are repairing and trying to do crack repair, and they unintentionally will lift it. It only takes 10 psi to start getting movement in a slab. Just be aware of that. Quality control. So there's many different ways to be able to verify if if you've addressed the crack properly. Again, we've talked about NDT. We talked about coring. I'm going to have some photos here. So we did this repair in the middle of nowhere. It literally was in the middle of nowhere. And the client said, we don't have time to core it, send off, crack, do compression testing. So I need you to fix this trunnion block. So there's a large motor trunnion on top of it, a bearing block. And we need to verify while you're on site that everything's been fixed. So we did impact echo before, and we did it after. And you can see there's a lot of material that's in the way, so you can't get to every single inch of it, but you could see that some of these PSIs, the darker the color, excuse me, the more closer to red it is, the lower the PSI. And you can see how significantly that trunnion block, and this is actually photos, kind of slice it, as you're looking through the thickness. So this is giving you different images because we found voids. That red area inside of it was actually honeycombing and voids, and then the epoxy injection was able to fill all of those. When you start the epoxy injection, in a lot of cases, in this one, you don't stop till you get it done because you want to make sure you keep those ports open. So I think this is 22 hours of straight injection going on to achieve these results. Client was thrilled, and the material's been working very well since then. We're going to jump in a little bit into case studies here. I want to be able to show, this is Hardy Dam. This is in Michigan. This is a mortar grouting. So we're working in a spillway. And so built in the 20s, 30s, somewhere around there. And so they needed to retrofit the spill tubes, which is where the water goes through the turbine, comes through and comes out the other side of it. So they added the steel liner. Well, the steel liner has a 1/4 inch gap behind it. Again, creates cavitation, creates issues along those lines. So when you install the steel liner, I'm just kind of showing that darker areas where the steel liner gets installed, we want to come along. There's the steel liner. Wonderful work environments. We were about, I think, 3 foot tall at the highest point there at some point. So we had 1,200 anchor bolts. We add 112 ports, grout ports, 3/4 inch. So these aren't very thick, wide, 3/4 inch diameter ports. And then here's a good photo of it. So all of those, you're holding on, you got the steel anchored to the concrete above it, and then everywhere where you see a white PVC, that's where we were doing the injection of the cementitious material. So, and here's the grout pump. I put something on here about a colloidal mixture. I won't go into it, but if the data sheet calls for a colloidal mixer, do not skip that step. This is a very expensive pump system that we had, a mixing and pump system, but it does a phenomenal job. And so this is the injection process. So the QA, QC after was, again, they're running impact echo, trying to find voids. They would identify where there's spots. We would use a mag drill and drill through, and you can see we pretty much had 100% success because you could see where we drilled in, and they drilled right through our, once you got through the steel, you could see the complete circumference of that hole on the right-hand side has been grouted, and that's been filled. So this next one is a confidential location, but this is a very large injection job. I just kind of re-highlighting some of the basics. This is a really good photo of a port being installed over the top of a crack. You can see that gentleman adding the ports as he goes along. The right photo just shows I got a nice setup. You have the head, the mixing head is sitting on the ladder, and then they have a hose leading to just allow them to kind of leave the injection hose or the injection head in one spot and to be able to move port to port without having to carry that around. So it's a nice adjustment. This, I wanted to show this one. Actually, I don't think I have the slide blown up close enough, but you can see, okay, why all these tubes? So what's actually happening in these solutions is actually voids in the concrete behind. It's not cracking. You're not seeing cracking. So they drilled in and we are repairing the voids with the epoxy injection. So this is almost like a packer was installed, and then you added these this tubing so that we can do the injection. So this gentleman, this is unintended consequences. So this gentleman is being shown, he's doing a fantastic job of doing epoxy injection on the left-hand side. On the right-hand side, this is the public display area. And well, unfortunately, if you talk about low viscosity resins, it will find its way through. So where the photos were mounted into the wall, the epoxy injection was able to reach where those anchors were installed and started coming out the anchors into the public viewing area. So almost too good of a job of doing injections. And then this is a great photo because he's using a GPR unit to determine where to avoid the steel. He cores into the concrete, pulls out a core, and then under black light on the right-hand photo, you can see that effervescence from the epoxy injection resin showing up. So he's verifying that the epoxy is reaching and filling that, and you're looking for at least 90% fill. The curtain wall grouting, I don't want to rush this one too much. We got 3 minutes, and then we'll leave open to answer some questions. But this is just a really good example of how curtain grouting works. So they're having water intrusion behind this masonry wall. So they're removing part of the bricks here so you could get to the concrete that's behind this masonry wall. They're having water push through. It's coming out through the bottom between the slab and the wall itself, causing a lot of problems for this school. So our team went in, drilled holes at intervals, and install these lances. So these lances will go through the concrete to the back side of it, because we don't want to fill the bricks in the concrete necessarily at the front. We want to make sure we get that curtain grouting, that urethane on the back side of it. You're creating these discs of urethane that will now be on the positive side, protecting the wall, providing waterproofing. So you go along, you inject all of these. You use a certain amount of time so you know how much material you're putting in. You want to make sure you get enough thickness. Remove your lances. So you go along and inject all those areas. You remove your lances, repair your holes. And then they're adding a cementitious, they're using a waterproof coating as well on top of the masonry. So they're adding a secondary piece because even though you're creating that barrier, this is additional protection for the new gym floor that was being installed. And that's what the project looks like nearly to completion. So something important I always want to point out when it comes to when you're below grade, so this is below grade, you have a water table level. When you're doing this injection, this repair, you're not magically drying up the water back there. You're just creating a seal in that area. So when you seal up this area, the water seeks somewhere else. So they actually installed a drain and a mechanism by which to collect the water in a controlled area close to that door. And so it wasn't building up a whole bunch of pressure. It wasn't sitting there and finding unintended consequences somewhere else. They built that into the design. You're able to, it no longer is leaking into the gym, but is being managed and handled in a controlled manner. So, hey, questions. Look at that. Right on time. 10 minutes to. So
Well, perfect. Thanks, Mike. Yeah, great
Jeff.
presentation. Now we'll definitely get to some questions. I got quite a few here from the groups, so I'll just start reading some. So here's one from Tyler. It says, regarding evaluating different methods for addressing cracks or voids. Oh, hang on a sec. Sorry, wrong question. What additional considerations are required for sealing actively seeping construction joints for urethane injection? Like, what do you typically do when you have a water pouring out of a joint, Mike?
Okay. Well, if you take that Hardy Dam, there was a portion that we did not show because we were fixing a ring beam and the water was shooting 15 foot across from that crack and hitting the other side of the wall under a lot of pressure. So a lot of times we'll actually go in and we may have to use a temporary hydraulic cement plug or an oakum soaked. If you take oakum, which is sometimes called horsehair, and you soak it in epoxy resin, we can jam that into an active crack if it's pushing out enough pressure, and that will expand and slow down that leak. And then we can use the properly. We'll pick the urethane material with a quick catalyst, a fast activating one, and then we're able to inject it in there and you stop that water flow that way. So,
okay, right. Perfect. How do you select positioning of injection ports? Why use it over the crack or on an angle? What's the difference?
So epoxy resins, when you're doing that, has a very low viscosity and you're sealing that crack up. So those are the epoxy resins are when you're putting it right over the top. And so you're sealing the crack itself with a putty material, epoxy like putty, and then you're using in select spots to get the injection to go through because that epoxy resin will travel through. When you're using a urethane, a polyurethane chemical grout, that's the ones that you're using packers and coming in at 45-degree angles. And what you're actually doing there is you're intersecting. So let's say your crack is 12 inches thick, your crack. You're actually going to try to intersect that crack at 6 inches in. And then as you're injecting, it should be traveling close to the same side on both sides of it. Maybe you don't have access. In most cases, you don't have access to the backside of that crack. So when you start seeing that urethane coming out of the crack itself, that kind of gives you a visual cue that, okay, I'm getting this crack filled. I can move on to the next port and start filling that up.
Very good. Michael asked for some cold weather repairs. Could you use the exothermic properties of epoxy to avoid heating the concrete before doing the repair?
Yes and no, but your number one problem is since if you are below the approved temperatures, it requires enough heat in the environment to get that catalyst going. So if let's say your epoxy resin says, hey, you can't use it below 40 degrees and it's 30 degrees and you start pumping it in there, that cold temperature is actually keeping that catalyst, that exothermic reaction from occurring. So it will never kick off at that. Some whatever. I mean, we won't get into it. Maybe when it heats up later, it may occur, but there's no way of knowing if that's properly occurring. So it's very important that you meet the temperatures. Very important. You don't know how many nights I've left my truck running with the epoxies in there because we're on the job site. We have to keep it at 70 degrees. So don't let your epoxies get cold. Your resins get cold. You got to keep that stuff warm as well. Good.
This is just a comment from Andrew. He said, Great discussion on curtain wall grouting. Seems to be the only method that really works for us. We've tried urethane grouting, but this works very well. So just wanted to comment on that, Mike. Another question here is, if you inject a crack where there's evident corrosion, will that stop the corrosion, or do you need to deal with the corrosion in some other way?
The injection will not stop the corrosion. So if you have the opportunity to be able to address that corrosion, that needs to be done as well, because you may fix that crack there, and that epoxy may be strong enough to deal with it at that point. But as it expands, that 300 tensile strength of concrete won't hold up to that expanding corrosion and will crack somewhere else.
So one of the questions was about aesthetics with the epoxies. When you're doing the surface seals and the putting anchors on there, is there anything you can do afterwards to make it more appealing? What's the process afterwards?
So there's two lines of thoughts there. If you're in an environment where aesthetics don't matter, then leave the epoxy paste there. It's just one extra level of coverage. If you are where aesthetics do matter, then there's a couple different ways of handling it. There are some epoxies that are more temperature sensitive, and you could if you hit it with a flame, it will kind of peel off and be less of an impact. If you're kind of those are really good. That's a really good choice when you're using in an area where you really need to focus in on aesthetics. If you're in an area of just moderately, then you can just take a grinder to it and you could grind that surface area.
Perfect. This is a question where I've seen contractors use a caulking gun for some kind of epoxy injection. Is this acceptable or a decent method?
Yeah,
what do you suggest?
Yeah, there's so many different versions of it. If you're using a caulking gun, typically if you got an A and B on each side and it mixes in the head, I've used that quite a bit. It's really no different than if you're using like a Hilti epoxy for anchors. And so that works well, but it's also based on quantity. So if you're doing repairs and use like small crack repairs, yeah, no problem. But if you're trying to do a large volume of it, the QC of a good epoxy pump, like the pumps that we use from Chemco, are just phenomenal. They have a 2-to-1 ratio. It's we have calibrations. We can do a lot of testing there, but you can do tens of hundreds of gallons, thousands of gallons. I mean, we've used thousands of gallons through those machines, replacement heads, all the rest of it. So it all depends on the situation.
Yeah, I imagine your hand would get sore using a caulking gun after doing 10,000 lineal feet of crack repair.
Yeah. Well, I mean, there's a point to it too. Is it's the equipment can be expensive, so finding the right contractor that has equipment is important. And I've seen the problem I have with caulking guns is if it really takes you doing quite a few of those cartridges. You got the time in between that you're switching out and you're doing different guns and all the rest of it. I mean, it's made for smaller repairs.
One last quick question here. What kind of structures mainly have you been using the curtain wall grouting system for? Have you seen them in steam tunnels and different things?
Yeah, no, that's great. We actually do a lot when it comes to basements in industrial facilities, especially. We do a lot of below grade environments, and then we also have done either steam vaults, as far as in universities. It's another good application, and then also like in the agriculture world, between the silos, a lot of times you'll have below grade. You'll have tunnels and the cones where they're collecting the grain, and the conveyors are all below grade as well. And traditionally, back in the day, they just let water kind of flow through there, but they're kind of, wising up and saying, hey, let's try to restrict the amount of water getting in. It creates a better product, less moisture, less concrete problems. So
perfect. Well, thanks, Mike. We're kind of running out of time here, but I just want to thank you, and we probably put too much There's a lot of information there in a quick amount of time, but thanks for your brief overview. As far as questions go, if we haven't answered them, Mike will get back to you. If your name's in the chat, we have your email address. Mike will answer them and get back to you after this is over. And if you think of any more questions, Mike's contact information is up here. This information will be provided in our post-event emails, along with links to the presentation slides that Mike was using. So you'll have both of those. If you have not done so already, please register for our next session in the series, Redefining Structural Integrity, using FRP to strengthen concrete structures. If you'd like to register now, please scan the QR code on the screen. Finally, Mike, thank you very much. Awesome presentation, and thank everybody for attending. Now let's go out there and save some structures. Thanks, Mike.
Awesome. Thanks, Jeffrey.